All right, we've made it to the end and we are starting our review for our end of year final. This video is going to cover the end of year review part 1. Again, I would consult your notes, work through these, do the best you can on working through these with what we've learned in quarter 3 with our geometry and our trigonometry. And then if you get stuck, you can work through this video. I'm just going to kind of work through the process, maybe remind you of some things that we covered in class. So let's just start with number 1. We're starting with dilation. So for the following, state all of the dilated vertices and then graph both the original and the dilated image. So it gives us here that it wants us to dilate by a scale factor of 2, and these are the original points, y, x, w, and v. Remember with dilation, dilation is just a change of size, so it keeps the same shape and the same proportions related to those lengths of sides. So if we want to take a figure and dilate it, we said each of the pieces have to change by the same scale. So if we're dilating by a scale factor of 2, that just means we take each of these components of point y, which are -2 and -1, and we're just going to find y prime, or the dilated y point, by multiplying by 2. So -2 times 2 is -4. And -1 times 2 gives us -2. So we're just multiplying or doubling each of these. X was given to us as -1, 2. So if we want to find the dilated image's x vertice, then we multiply each of those by 2, and we can double those. And we're going to do the same thing for each of the points here. So W is at 2, 0, which makes W prime 4, 0, because again we're doubling, and if you double 0, just 0. V was at -1, -1. So V prime, if we double each of those, is -2, -2. Now again, your scale factor is not always 2, so make sure you use your scale factor. That was part A. They wanted us to find those vertices. Part B, go ahead and graph both the image and the dilated image. So if we look at this, if I want to graph the original image, y is at -2, -1. And we always make sure that we label these when we graph. So x is -1 up 2, and w is at 2, 0, and v is at -1, -1. Again, if you connect those dots, right, in the order given, that gives you your original polygon. Then you can go ahead and graph the prime dots. So y prime is at -4, -2. So notice out here we've got y prime. X prime is at -2 up 4. W prime is at 4, 0. And -2, -2 puts us at V prime. Notice it keeps the same shape. Those lines that you're creating remain parallel to the original ones. Oh, unless you draw it like I do. Yikes. And then you have your dilated image there. On the next ones, you're looking at similar figures, just related to, right, similar figures are just an image that's been dilated to another image, so different size, but those proportions have to stay the same. So notice the angles stay the same, and then again their proportionality. Sometimes you can tell just by looking at them. If not, we set up a proportion with corresponding sides. So notice here, if I'm looking at these two shapes on number 2, I'm looking for the relationship here, and again, if I can tell what it's growing by, I can go that direction and just identify the value. But if not, we set up proportions here with corresponding sides. So we would say, well, 12 is to 8 in the same way that this side should be to its corresponding side. And it's weird to use a question mark in an equation, but since that's on our diagram, I will. And then we worked a lot with cross multiplication. So once you have your proportion here, we go ahead and we cross multiply there, and then we just continue to solve. So if 8 is multiplied by that unknown, we divide by 8, and if we take 144 and we divide by 8, then we end up with 18. On number 3, again, this one you can readily see the change here, or the relationship. So if you notice, 16 corresponds to 8. Well, 8 is just half of 16, so we know that this image right here is just half the size of this other image. So if I want to figure out what question mark would be, well, 1/2 of 6 is 3, So in this case, we can just identify that as 3. On number 5, again, same idea. This one just has a binomial representing the unknown. So if we're looking at this, we could again say 16 is to 24 as it corresponds there. 16 is to 24 in the same way that 12 should correspond to the 2x plus 2. And again, we cross multiply, so we start with maybe our 24 times 12. That gives us 288. And then this is the part that might look a little different, but it's the same idea. We have 16. You just need to make sure you multiply that by the binomial of 2x plus 2. Now again, you could divide by 16, but if it helps you just to distribute this first, go ahead and do that. So you'd have 288 is equal to 32x plus 32, and then we're just solving. So subtract the 32 over here to isolate the x. We end up with 256, it looks like. And then we take 256 and divide it by 32. And we end up with 8. Okay. Number 6, again, very similar. It says solve for x. The triangles in each pair are similar. Now just be careful, the triangles or the shapes are not always oriented the same way. So when we look at this similarity statement, we need to make sure that we're understanding which part relates to which part. Remember, the order you write a similarity statement in, those angles, they relate to these angles over here. So W is going to relate to G, V to F, and so on and so forth. So when we look at this, it helps me if I'm using figures that are oriented different ways, if I just draw. So this one's starting with W to V to U. So W, then it goes to V, then it goes to U, right? The next one, it looks like, starts with G. So G relates to that W I circled, and then it goes to F, and then it goes to E. So notice that first movement or side it creates relates to this other first side it creates. So I'm going to set up my proportions saying, well, 36 is to 66. So this guy is to this one. As this one would be to this one. So 66 would be to the binomial 16x minus 7. Then again, this one we solve using cross multiplication. So 66 times 66, 4,356. And then again on this diagonal you have the 36 times the binomial 16x minus 7. Okay, and again, if it helps just to distribute that as you're solving, you can do that. 36 times negative 7 leaves us with negative 252. Okay, and then we're just solving, so we're going to add 252. We get 576x. We get 8, 0, 6, 4 when we add that together. Oops. And then we divide that. And it looks like we end up again with x is equal to 8. So again, the goal on that is recognizing when you have similar figures, the sides have to be proportional. So you set up a proportion and then you solve. Moving on to the next page, the next thing we covered was our triangles, our trigonometry. And the first thing we did is we reminded ourselves that whenever you have a right triangle, right, we said, okay, well, if it's a right triangle, then you can always do the leg squared plus the leg squared, and that will be equal to that hypotenuse squared. The hypotenuse was always the longest leg. Oh, that's weird. And is always opposite of the right angle. Okay, we know that that would be a right triangle. We also said you can go backwards and test to see if it's a right triangle if you're unsure, or if you want to see if it's an obtuse or an acute triangle. So we said, well, you take one of the smaller pieces, right, and lots of times we call that like a squared, and you do add it to the other small side, b squared, and then we see what happens in relation to c squared. We said if that's equal, then we know it's a right triangle. But if the c squared's bigger, so you perform that same experiment and the c squared is bigger, then we know that that creates a really long side, which means really long, or not long, big angle. So it's obtuse. And then kind of in that same realm, if it's the other direction, so the a squared plus b squared is larger and that c squared is smaller, then that makes it an acute triangle. So we call this the converse theorem over here because you're kind of going backwards to tell which kind of triangle it is. So number 7 and 8, very similar. I'm going to work through number 7. If you look at this one, we are going to take the two smaller sides. If you can't tell which are the two small sides, you do need to plug those radicals into your calculator and kind of see. This one's about 8.66. Square root of 26, that's just a little bit bigger than the square root of 25, so that's going to be 5 point something. So we know that this is a small side and this is a small side, so we're going to take that and do this test. Square root of 26 squared plus 7 squared, and then we're not sure if it's equal to or greater than or less than this longer side over here. And again, we're squaring, oh, sorry, so many parentheses there. I'll try not to confuse you. We take this side and square it, okay? And again, you could just plug it into your calculator if you'd like to. Remember, a squared and a square root cancel, so that's like 26 plus 7 squared is 49. Again, we're still unsure if these are equal. When you square this, that's like 25, maybe I'll write it up here, 25 times square root cancels with the radical, and you have 3, so this is like 75 over here. 26 plus 49 is 75 as well, so notice these are equal. And remember, if it's equal, we said, well, that means that it's a right triangle. Okay, so you'll do the same thing with number 8, setting up to see what kind of triangle that is. Number 9, you're just using the Pythagorean theorem, so just make sure that we're comfortable with practicing through that. Number 10 as well, so I'm going to work through number 10, but again, same idea. Just make sure it's always leg squared plus leg squared equals hypotenuse squared. This one wants us to find the hypotenuse, which they're calling little c. So we're given the two leg lengths here, so we're going to say 4 squared plus 6 squared is equal to the unknown c squared. And then we simplify, right? 16 plus 36 is equal to c squared. If we add 16 and 36, we end up with 52. And then if we're solving for c to undo a squared, right, we square root. So we get c is equal to the square root of 52. Now it asks us to leave it in simplest radical form right here, which means we don't write that as a decimal. We just break that down with our little factor tree. So this is the same thing as 26 times 2. And 26 can be broken down into 13 times 2. So this 2 right here comes out front, and it looks like we've got 2 square root of the 13, which stays inside. This one told us it was meters, so I'm going to write m right there. But again, just applying that Pythagorean theorem, making sure we're comfortable with that. Okay. These last ones are related to the trigonometric functions that we learned. So remember, we learned sine, cosine, and tangent. And we said the relationship here, they each just connect two different sides of the triangle. And notice on 11, 12, 13, and 14, you have an angle instead of two sides. So you can't use the Pythagorean theorem just to start out with on these because you don't have two sides. Instead, you have an angle and a side. And then we can use those two pieces to find that third side. So I'm just going to write this up here so we remember. But SOHCAHTOA, right? So sine is always the opposite leg over the hypotenuse. Cosine relates the adjacent leg to the hypotenuse, and tangent relates the opposite leg to the adjacent leg. So the first thing you have to do is decide which trig function to use, and then they all work the same algebraically. So on this first one, number 11, again, we're looking at an angle. Here's our reference angle. So if that's the angle I'm using, again, I'm going to label the parts. Here's the hypotenuse. And the leg that's sitting right next to my angle is called the adjacent leg. Now we know that the opposite leg is over here. The reason I'm not really labeling it is because I don't know anything about it, and I'm not being asked to find that length, so I'm not even going to worry about looking at the opposite leg. I'm going to find the trig function then that uses adjacent and hypotenuse. So if I look over here, oops, I scrolled a little. Adjacent and hypotenuse would be the cosine function. So we're going to set up an equation that says cosine of our angle, always of the angle, is equal to adjacent, which is 19, over the hypotenuse, which is x. Now remember, if your variable's in the bottom, this one's a division problem eventually, right? So we said we had to multiply by x to get it out of the bottom, and then you have x cosine of 52 equals 19. We want to get x by itself, so we divide the cosine of 52 to the other side. And again, that becomes a calculator problem, and you just need to double check that your calculator is in degree mode. And we do 19 divided by the cosine of 52. We're asked to round to the nearest tenth, so we go ahead and round this to 30.9. Okay, 12, very similar. I'm going to set this one up and then you can work through and solve. This one right here again, here's my reference angle. Notice the hypotenuse is out here. I don't know anything about it. I'm not trying to find it. So this guy, I'm going to ignore the hypotenuse, and we're going to use the opposite leg to help us find the adjacent leg. So again, opposite and adjacent, it looks like we're going to use tangent right here. So we're going to say the tangent of the angle is equal to opposite, which was 19 over x. Actually very similar to number 11. And then you're going to go ahead and keep solving that until you get your final answer there. 13 and 14, again, same idea using SOHCAHTOA, but this time we're going to solve for the angle. So remember, if we don't know the angle, we still set up our ratios the same, we just have to use the inverse trig function. So again, here I'm going to label the pieces. It looks like we're given the hypotenuse and the opposite leg. So that O and H comes from the sine function in SOHCAHTOA. So we're going to do sine of the question mark, or the angle, is equal to opposite, which is 8 over 10. Now in order to solve for the question mark, because it's stuck to sine, right, we said you have to do the inverse to get rid of that. And if you do it to the left side, you also have to do the inverse of the right side. So essentially we just have question mark is equal to the inverse sine of 8 over 10. And remember, the inverse is just second sine, 8 divided by 10, and you're looking at 53 degrees. It asks us to round to the nearest degree, so I'll just round it to 53 degrees. Okay, again, 14, similar idea, just look at the components that are given to you. So you're solving for this angle, and it looks like, again, you have the hypotenuse, but this time you have the leg next to the angle you want to find, so that's the adjacent leg. So A and H, if we look at our SOHCAHTOA here, we're looking again at A and H, which is cosine. So this time you're going to say the cosine of the question mark would be equal to 9 over 30, and then go ahead and solve for the angle there. Last one on this page, so this one is just relating the three together, very similar to an ACT type question that you would see. It gives us that the cosine of an angle, again that symbol means theta, it's just an angle, is 8 over 15. Whenever I see cosine, one, I think, oh, it's a right angle or a right triangle, and secondly, I think this is adjacent over hypotenuse. It just gave us two sides of our right triangle. And then it wants us to find the sine and the tangent ratios. So what we're going to do again, and we did this a little bit in classes, sometimes it's just easy to build your triangle and call one of your angles theta, it doesn't matter which one, and then label your sides. So we know the adjacent side is 8, so adjacent leg right there, and the hypotenuse here is 15. Okay, the reason we set that up is just to make sure that we use the Pythagorean theorem correctly. We need to find this missing side so that we can set up our other two ratios, sine and tangent. So to do that, again, we're going to use the Pythagorean theorem, because all we want to do is find a third side when we already know two of them. So we do leg squared plus leg squared is equal to hypotenuse squared. And then we go ahead and solve. So x squared plus 64 equals 225. Subtract the 64 to both sides. Whoop, that's a little bit messy. And we get 225 minus 64 is 161. Then we square root. Now if we could, we would simplify, but 161 doesn't have any nice pairs, so we're going to leave it there. So this side over here is square root of 161. Now that we know all the sides, we can set up our sine ratio and our tangent ratio that it asked for. So remember, sine is always opposite over hypotenuse. So the opposite of the theta we drew in here in our triangle, right, is the guy that we just found. So the square root of 161 over the hypotenuse, which was 15. And then tangent, our other trig ratio, is adjacent. So again, that means next to. That one's the 8 over the hypotenuse, which is 15. So always relating back to SOHCAHTOA, making sure that we're comfortable with using that. All right, the last page we are just using trigonometry to find different parts of the triangle, and then applying what we've already talked about here, and then parallelograms. So let's touch on this real quick. Number 16, a 40-foot flagpole casts a 25-foot shadow. It first asked us to draw and label a diagram, so we remember how good we were drawing these. So we've got a 40-foot flagpole, so here's our flagpole. Whoop. It's a flag. And it's 40 feet, so I'm going to label that. And it's casting a 25-foot shadow. Find the shadow of a cast by a nearby building that is 200 feet tall. Oh dear, this is not drawn to scale. Here's my 200-foot tall building. And it's casting a shadow over here, and we don't know what that is, so I'm going to write X feet. Now, clearly, that building is much taller than that flagpole. Okay, so again, we're just using the proportions that we looked at on the first page. Notice these are creating like similar figures, right? Those proportionalities should hold. So we're just going to say, well, 40 is to 200, as the shadow is to this shadow. And again, we like proportions because if you're more comfortable with doing the flag over his shadow to the building over his shadow, you can do that as well. Your proportions will come out the same. So 200 times 25, that gives me 5,000. And I get 40 times x. We divide that by 40. And it looks like the shadow is 125 feet long. Okay. Number 17 is going to be very similar. So if you're looking at Aaron, who is 1.6 meters tall, casting a shadow that is 1.25. So here's Aaron, is 1.6 meters tall, has a shadow that's 1.25 meters. Her shadow extends to the end of a tree's shadow when she stands 4.7 meters from the tree. So notice here we've got a tree. And it looks like they said that her shadow extends to the end of a tree shadow. So their shadows look like they're overlapping here. They end at the same place. And it looks like so this little piece right here is 4.75 meters away from the tree. And what is the height of the tree? So again, notice you've got kind of two triangles here. We could say, well, this height of this tree is to this height of Aaron, so h is to 1.6 as the height of the tree shadow, or the length, I guess we would say. And if you look at the full length of the tree shadow, you've got to add those together. So if you add that together, that's 6 meters. So the full one is to Aaron's. Again, notice that proportion that we set up. So the height of the tree to the height of Aaron, tree shadow to Aaron's shadow. Then we go ahead and we multiply. So 1.6 times 6 gives us 9.6 is equal to 1.25 times the height. So we divide by the 1.25. And the height of the tree, according to this, is about 7.68 meters. Okay. All right, let's look through these last couple. So number 18, find the area of each triangle. Remember, area of a triangle, anytime you hear that, should say, okay, that's 1/2 the base times the height, or base times height divided by 2, however you want to think about that. We're going to round intermediate values to the nearest tenth. That just means as you're going through the problem, if you need to round, stick to the nearest tenth. So here we go. We have our triangle here. It looks like we have a base of 10.8. So if I'm actually calculating the formula, I already know that this is 10.8. There's my base times my height divided by 2. I just don't know what that height is, so we need to find that in the triangle. So if we go ahead and we drop an altitude down here, right, this would be like the height of our triangle. Because we've got an isosceles triangle, meaning both of those lengths are 12 on the top there, when we drop this altitude, it actually cuts this bottom in half. So if that full bottom length is 10.8, then half of that is going to be 5.4. Now, why do I want half of that? Well, the reason I do is because this is a right triangle, and we know how to use the Pythagorean theorem with a right triangle so that I can find the height. So I'm going to come over here off to the right, and again, one of my legs is this height, so I'm going to say h squared, leg squared, plus the other leg is just half of this guy down here, this one, 5.4 squared is equal to the 12 squared. The 12 is the hypotenuse of that little right triangle that I just drew. So again, we've got h squared plus, we're going to take 5.4 and we're going to square it, which is 29.16 is equal to 144. And then we go ahead and we take 144 and we subtract out the 29.16. Maybe. And it looks like our height is the square root of 114.84. Now it asks us to round intermediate values to the nearest tenth, so that's where it's saying you only need to round to about 0.8. But if we take the square root of 114.8, the height here, sorry I didn't show that work, is equal to 10.7. So I'm going to put 10.7 in here as my height. Okay. And then we just calculate the area. So 10.8 times 10.7 is equal to 115.56 divided by 2. And the area here should be about 57.8. And it doesn't give us any units, so I'm going to write units squared just so that I know they're square units, meaning it's an area length or area value instead of a length. Okay? All right, last ones we're dealing with just parallelograms. Remember that parallelograms, they're just like a squished rectangle. So all the things you'd say in a rectangle, right, if we were to squish that down, like these two sides are the same length, these two sides, opposite sides are always the same length. And then we decided that opposite angles are always congruent. So if we're looking at this number 19, we know that this angle over here, W, would be equal to this angle, Y. If they're angles that are next to each other, so these two, they need to add to 180 degrees. So we're going to set up a little equation and say 8x minus 7 plus 115 should equal 180 degrees. And then it's a matter of solving that. So notice you have a negative 7 and a positive 115. So we've got 8x, and if we take negative 7 and add 115, we end up with 108. And then we continue to solve, so subtract 108. What's that, 72? And if we divide that, x is equal to 9. So again, if they're opposite the diagonal, they're equal. If they're next to each other, we call them consecutive angles, then they add to 180. Number 20, again, this says this length is 22, and it wants us to find the value of x here. Well, we know that opposite lengths in a parallelogram are going to be equal, so we're just saying, well, what value of x would make these equal? Some of you are really good at doing this logically, or you can set up your equation and then just go ahead and solve. So 24 must be equal to 6x, and divide that by 6, and that means that x is equal to 4. Don't overcomplicate those, just setting it equal and solving. 21, again, remember that diagonals of a parallelogram bisect each other, so we know that this piece would be equal to this, and then this piece right here would be equal to this piece. So they bisect each other, they cut each other in half. So I'm just going to label the parts that are given. It says that L to J is equal to 20. So we've got L right here, all the way to J is equal to 20. So I know that full thing is 20. Maybe I could split that up and even say, well, this is 10 and this is 10, right? If I look at S to J, so if we're looking at S right here to J, it tells us that's equal to 2x plus 10. Well, you'll notice, right, we know that this is 10, and this says it's 2x plus 10. If those need to be equal, and again, some of you will be able to do this logically, but if you set those equal to each other, and then solve, if we minus 10 and minus 10, it says 2x is equal to 0. Well, anything times 0 is 0, right? Or in other words, divide by 2. But x in this case is equal to 0 to make that true. Okay? Lots of properties there. Again, just making sure that we remember parallelogram properties, how to use the sine, cosine, tangent rule, and then also looking at our dilations and similarity.